Welcome to Pomodoro Joe for Saturday, April 15th, 2023. Today we're doing LeetCode problem 2218, maximum value of K coins from piles. This is a hard problem. So there are n piles of coins on a table. Each pile consists of a positive number of coins of assorted denominations, so they're different values. In one move, you can choose any coin on top of any pile, remove it, and add it to your wallet. So given a list of piles, where piles index I is a list of integers denoting the composition of the ith pile from top to bottom, and a positive integer k, return the maximum total value of coins you can have in your wallet if you choose exactly k coins optimally. All right, so said another way, we have a bunch of piles of coins on the table. Now we can only take coins off the top of each pile, and we can take up to exactly k coins. Not up to, we actually have to take exactly k coins. So we can take exactly k coins, we have to take them off the top of the pile. But when you take one off the top, the coin below it becomes the new top of that pile. So for example, you can take coin 1 or 7, or you can take 7 and then take 8, or take 1 and then take 100. So the tricky part is we don't really know what's beneath each one of these coins. I mean, we do, but we will be taking coins off the top in order to reveal the more valuable coins below. Okay, so we will put 25 minutes on the Pomodoro timer and get started. So let's just do this in the straightforward manner. We will actually do what they tell us to do. We'll take each move, we can take one coin off the top of any pile, and then we'll recurse. So the plan is we'll take a coin off the top of a pile, then we need to reduce the number of coins we're allowed to take, so we have to reduce our k by 1. So we'll take one coin, reduce our k by 1, and then we'll call this same function again. Give me the maximum for the remainder of the coins with the remainder k, or whatever is left of our k. That seems pretty straightforward, so let's give it a shot. So we'll have some result that will start at 0. We'll return the result at the end. And now we actually go through. For each one of the piles, we'll choose that pile as potentially the one we'll take a coin from. So we'll actually go through every pile and say, we'll take one from pile 1, and then we'll recurse. But then we actually have to put that one back on top of pile 1, and then we'll take one from pile 2, and we'll say, what's the best answer we can get from the rest of the coins and our remaining k. Then when we get that back, we have to put our coin back on top of pile 2, so we can take one from the top of pile 3 and say, now what's the best answer we can get from the remainder here. So it's going to be a little bit tricky because we'll be taking coins off, finding the best answer from the remainder of the coins. Then we have to put that coin back so that we can take one off a different pile. All right, so let's see, for pile index, in range, length of our piles. Let's see, so we'll actually take a coin off the top of this pile. So our coin will be equal to the top of this pile. So we'll just pop a coin off the top. All right, so we pop a coin off the top of this pile. Now we can say our result, or this option for our result, will be equal to this coin plus whatever we can get from the rest of the coins. So that's going to be self, and we have to call max value. We'll still pass in the same piles, and this time it'll be k minus 1 because we've taken one coin already. Now once we have our option, our result will be the maximum of our current result, or this option. And then finally, we need to put the coin back onto this pile. So let's see, that means this pile at this pile index equals the coin plus the pile at this pile index. Okay, so this might look a little weird in the way that I'm doing this, and I'll go through it really quick. So we're doing exactly what they say. We choose a pile, we'll take a coin off the top. So pop 0. So we have to do pop at 0 because the top is the index 0 in this case. So we'll pop a coin off the top, so index 0. Then we will say, well, we have this coin. What's the best result we can get from the remaining coins, or what's left in our piles, and this k reduced by 1 coin? And whichever result ends up being best, we'll hold on to that. But then we have to put the coin back on top, because this piles is a list of lists, which means it's actually shared across different calls of this function. It's sort of one place in memory that's shared every time you make this function call. So this piles here is actually a modified version of the input piles here, because we've popped one off the top of this pile. Now that actually works to our advantage, because when we pop this one off the top, we don't need to make a copy of the piles. We can actually just use the same piles in memory. But it does mean we have to fix it up at the end. We have to put our coin back on top, so that when we pop off of stack 2 or pile 2, we will have a restored stack 0 or in stack 1. I know that doesn't make a ton of sense. Let me put it this way. Let's say you actually have a bunch of coins on the table. You can take one coin off of stack 0 or pile 0. Then you can go through the entire set of piles and pull coins off, put them in your wallet. But in order to try again, you've got to put all those coins back so that you can try starting at pile 2 and then go through the entire algorithm again. So we have to keep putting this coin back on top so that we can do the recurse properly. Okay, let's just try this. All right, there are a couple things that I'm missing. I should have thought about this. I'm missing my base case, and I'm missing the case where we don't have any coins left on a pile. So let's do this. So if we don't actually have a pile at this index, or if the pile at this index is empty, then we'll just continue. All right, and the other thing I don't have is my base case up here, which is something I broke my own rule. I should always check the base case. So if k is equal to 0, we can't choose any coins, so we have to return 0. All right, let's try that again. All right, so this works. All right, so we have our base case. If we don't have any coins that we're allowed to take, we have to return 0. Otherwise, we'll go through every pile. We'll check to see if there's actually a coin left in the pile. If there is, we'll take that coin. Then we'll say, what's the best we can get with this coin plus the remainder of our coins? We'll take that best result, and then we'll have to put our coin back so that we can try the next pile. All right, let's submit this and see how we do. Taking a long time. Oh, and we don't pass. We run out of time after only 4 test cases. Wow. All right, so I'm going to use this test case as our new, I guess, bellwether. I don't know what the word is. Okay, so this takes too long. One thing we can try to do to speed this up is use some dynamic programming. Unfortunately, normally in this situation, I would use the cache function decorator. Now the cache function decorator will basically say for any given input, if I've already calculated the output, I won't do the calculation again. I'll just use whatever I've cached for that return, and I'll return that. Unfortunately, cache doesn't work with lists. It has to have a hashable data structure or value, and in this case, a list will not work. Okay, so how do we speed this up? Well, one thing we're doing here is we're actually modifying these piles. That can be slow. So instead of modifying the pile itself, what if we just kept track of what is the head or the top of the pile? So let's do that. Instead of popping and pushing piles, let's just keep track of where the head or the top of our pile is. All right, so let's do something else. That means we'll need a different function. So we will make an internal function for this. All right, so this will take a top of pile indices and the remaining k. And then the rest of this will pretty much be the same. So we will have to make a couple modifications. Let's do this now. Okay, so this is our new function. We have the max value of coins recurse, but now it takes a top of piles index or indices. So this is going to be an array that tells us what is the index that represents the top of this pile. So it's going to start as 0. So the top of every pile is the 0 index to start. All right, so the main things that we're changing here, instead of checking to see if we have a pile at all, it used to say if not pile. Now we have to check to see if the length of our pile, or the maximum pile index here, is equal to the index that we're at. That means that we've reached the end of our pile. All right, now we'll still pop a coin, but instead of doing a pop, we'll actually just grab it at this top index, and then we'll increment our top index. We'll add 1 to the top index. So that's the same as doing a pop. Then we will do our recurse, but we'll pass in the indices, and then we will put the coin back by basically saying, oh, the top of our index is actually 1 less than it used to be. All right, let's see how this does. Taking a long time. I'm not too convinced that this is going to work. And we get another time limit exceeded. Okay, so this isn't going to work as it is. What else can we do here? Well, let's see, the top pile of our indices, this one might be easier to do a key value pair. So let's try that. So in this case, we can have some dynamic programming. It's going to be an empty dictionary. Then we'll say, all right, we need a key. So our key, again, it's got to be a hashable value. Well, we can take this top pile index array and we can turn it into a string. This is really ugly, but you can do this. So you'll take a string of this top pile of indices. And then we'll also need our k. So now we're saying our key is a tuple of a string version of this array and our remaining k. Oh, that's one thing I wasn't doing. I actually have to change my remaining k. All right. So now that we have our key, let's check. If key is in our DP, then we'll just return DP at this key. All right. Now, if it's not, I should do this. Okay, so DP of key here equals 0, and then we do our return. And then down here where we have this return, we see DP of our key is equal to this result. So yeah, let's give this a shot. Oh, we're getting the wrong answer by a lot. So I must have something wrong with my indices. Let's check this out. I think it's this guy here. Let's see, if the length of our pile is equal to, I should say, is greater than or equal to, or less than or equal to. Yeah, that means we've passed the end of our pile. Okay. Okay, let's try that. Okay, it's working and we pass all our cases. Let's submit this, see how we do. And we still have a time limit exceeded, but we did a lot better. We're beating 77, or we're passing 77 out of the 122 test cases. So now this becomes our new benchmark. Okay. Now at this point, speeding this up is going to be hard. Now, one thing to note, I should have mentioned this at the beginning, but I'll mention it now. This is actually doing things in a very particular order. We're taking one coin off the top of the first stack, then we're recursing. Then we'll take one coin off the top of the second stack, then we'll recurse. Now what's happening here is when we take one coin off the top of the first stack, and then one coin off the top of the second stack, our end result is still this case. We have one coin missing from the first stack and one coin missing from the second stack. And that's really the only case we care about, this end result. We've taken two coins, one from the first, one from the second. However, in our recursive calls, it's also considering, well, what happens when we don't take one from the first, but we take one from the second first, and then we take one from the first. So we're actually doing the same end result in two different ways. So our end result is that we have these two coins, one from the top of the first and one from the top of the second. But we got there by taking the first and then the second, but we also got there by taking the second and then the first. And now we don't really care how we got there. We just care what the end state is. So now we're doing this multiple times for the same end state. So what we really want to do is just find all the end states and not care about how we got there. Okay, so that being said, I'm basically going to have to throw this whole thing away and start over. So with that, let's throw this away and start over from scratch. All right, now we only have 6 minutes left on the Pomodoro, so I don't know. Maybe now's a good time to take a break and we'll come back and start again. All right, when we left off with this one, LeetCode 2218, we were running out of time. So let's restart from scratch. Put 25 minutes on the Pomodoro timer and start again. In our previous solution, we just went through and followed the example they gave here, where we went through each stack one at a time. We would pop one off the stack, then we'd recurse on the rest. We'll take a similar approach in this new solution, but the key difference is we won't be going through and popping one off at a time and recursing on the rest. We will go through one stack at a time, popping one off, and then recurse on the rest. So this should help us get to our end states faster and not through multiple paths. So in this one, we will still have a recursive call, we will have a recursive function, but instead of going through popping one coin off or taking one coin off each stack, we'll go through each stack at a time and then recurse on the rest of the stacks. It's a slightly different way of thinking about this problem. So let's have a new recursive function called max value of coins recurse. And instead of taking our piles here, we're going to take which pile are we currently processing. So we'll call that the pile index. All right, and we still need our remaining k. Okay, so which pile are we currently processing and how many coins can we take? All right, if we are out of piles or out of coins, we'll have to return 0. So this is our base case, right? If our remaining coins is 0, we'll return 0. We can't take any more coins. Similarly, if our pile index, like the pile that we're currently processing, if that's greater than or equal to the number of piles that we have, we also return 0. Okay, now that we have a pile that we know we can process, we might need to check to see if it's empty, but I think we can get to that when we do our recursive calls. All right, so how do we process this pile? Well, we'll go through, we'll take either 0, 1, 2, 3, 4, up to k coins off of this pile. But this pile might not actually have k coins. So let's just see how many coins can we take from this pile. So let's see. So how many coins are in the pile? Maybe I'll call it a coin count. Let's just grab our pile to make this easier. So we'll have our pile itself. That's going to be the piles at this pile index. So this is the pile of coins that we're currently working with. So how many coins are in this pile? So that's just the length of this pile. Okay, so let's see. What's the maximum number of coins that we're allowed to take from this pile? Well, that's either the number of coins in the pile or the number of coins we're allowed to take, whichever one is smaller. All right, so coins count is the number of coins in this pile, and the max coins are the number of coins we're allowed to take from this pile, and that's whichever is smaller, the number of coins we're allowed to take or the number of coins left in the pile. All right, now we're going to go through our coin pile and take one at a time and possibly recurse on the remainder of our piles. All right, let's see. So we'll have some result and we'll start at 0. At the end, we'll return our result. All right, now we need to go through our pile here. For coins taken, I'll just call it index. That's just easy. For I in range, the number of coins that we have, or the max coins that we're allowed to take. So I'll call it max coins. So now we're going to take a coin off the top, or we're going to take the next coin in our pile here. Okay, so for every index in our range of the number of coins we're allowed to take, we're going to grab that coin at that index. Now, if we grab a coin at this index, it means that we had to have grabbed all the coins above this index. So let's just keep a running total here of all the coins we've taken off of this pile so far. Starts at 0. And instead of saying coin is equal to this pile index I, we'll just say the total is equal to, or we'll add this coin to our total. All right, so now we've taken I number of coins off of our total. Actually, it's I plus 1 number of coins taken. So let's see. Let's have a coins taken. That's going to equal to this index, because we're starting at 0. We're going to take coin at index 0, which means that we've taken I plus 1 coins. So let's see, our new remaining k. That's going to be this remaining k minus the coins taken. All right, so that's how many coins that we're still allowed to take. So at this point, we can do our recurse. All right, our option now is to do the recursive call here. So we'll take our total and we'll add the recursive call. So how much can we get from the remainder of our stacks and the remainder of our coins? So let's see. Now we're going to go to the next stack. So our pile index plus 1 and the new remaining k. And then our result is just going to be whichever one's better, our current result or this new option. All right. And now out here, we will have to do our initial call. We'll start at stack 0, and the remaining k is just going to start at k. All right, let's go through this really quick because it is confusing. We're going to have this recursive call. We're going to go through one pile at a time, take as many coins as we can from that pile, but as we take our coins, we're going to try all the recursive solutions. So let's see, if we have no more k, no more coins that we can take, then we have to return 0. If we have gone off the end of our list of piles, that means we have no more piles to choose from, we also have to return 0. Otherwise, we're going to grab this current pile, see how many coins are in this pile. So we can only take up to that many coins or up to the remaining k. So we cannot take more coins than are in the pile. We also can't take more coins than we're allowed to take. So that's going to be our maximum coins. Then we'll start a result at 0. Oh, I think this is going to have to change. So we start a result at 0. Then we'll say, okay, what's the total of the coins that we've taken from this pile? Now we'll go through and take off all the coins we can. So we'll start at 0, we'll go to the maximum number of coins that we're allowed to take. So we'll grab the coin off this pile's top, or the one at index I. We'll add that to the total coins that we've taken from this pile. Then we'll add that to the total coins that we've taken. So basically, we've taken I plus 1 coins off this pile. Because when I is 0, we've taken 1 coin. When I is 2, we've taken 3 coins, so on and so forth. Okay, so our new remaining k then becomes the remaining k minus the number of coins we've taken from this pile. So then our option here is to take the coins off of this pile, so that's our total, plus whatever we can get from the remaining piles. So we're going to go to the next pile in our list and pass in the remaining k to see how much can we get from the remainder. And then we just choose what gives us the best result, either the current result or this new option. Now, one thing that we're missing, and this is important, we are missing the very first case, and that is, let's not choose any coins from this pile. So we're going to start by choosing the coin on this pile at index 0. But what if we don't want to choose any coins from this pile at all? That means we need to do something before we go into this for loop. So we can do that out here at this result. Let's just say, let's not choose any coins from this pile, which just means we'll move on to the next pile. So we'll take this recursive function, we'll say pile index plus 1, but then we'll pass in the same remaining k. We don't actually need to take anything from this pile. Okay, let's see how we do. It's taking a long time. It's a good sign and a bad sign. It's bad because it's taking too long, but it's good that we haven't thrown any errors. All right, so time limit exceeded. Now we can use my caching trick here. So, because this function takes in lists, we can't do caching. Dynamic programming becomes hard because it's hard to create a key for this input value. But in our internal function here, we have 2 simple values. They're both integers. We have a pile index and a remaining k. These are completely hashable. So now we can use caching to store our values. So we can say from functools, import cache, and then we will use the function decorator at cache to decorate this function. So that should speed us up. Let's see how we do. And we pass. Let's see if we can pass all of the tests. And we pass. So we do okay. We beat 54% for runtime and 16% for memory, so that's not too bad. Now, one thing we can do, and I won't go through it, well, I'll show you really quick. All right, so let's try to just eliminate some of these small things, like the length calls, the min call, and the max call. Sometimes that makes a difference. So let's just keep a length out here. All right, so we'll just keep, let's say, length of pile in piles. Okay, so we'll calculate this pile length once, which means that we don't have to call this every time. That's this one. All right. Also, this length of piles, that's just a static constant, so we can say call it pile count. How about that? All right. So that saves us another function call. And then we still have this min and this max. So, all right, this will be remaining k. So we'll just do our own min here. So the remaining k, if remaining k is less than coins count, otherwise it's coins count, and same with the max here. We'll just say result will equal result if result is greater than option, else option. Okay, a couple function calls that we save. Let's see if this does anything. And that's a huge win. Holy smokes. Who would have thought? So now we're beating 96% for runtime, almost 97% for runtime, and 6% for memory. Wow. I never thought that making little adjustments like that would make such a huge difference. All right, well, there's still about 3% you can gain here, so give it a shot. See how you do. Again, this is LeetCode. What is this one? 2218. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.